Dear students, welcome to SAIMEDHA Koti, Hyderabad. Now, I am going to discuss an important topic in communication known as sampling. So, what is the topic of the discussion? Sampling. See, generally many students feel difficulty with sampling, but I am confident that after listening the lecture, yes, you will fall in love with sampling, right? And if you want to understand how sampling is done, you must know some basics. What are the basics required for understanding the concept called sampling? Let us see. See, the first basic required is how to calculate the continuous time Fourier transform of periodic signals. Continuous time Fourier transform of periodic signals. See, the first question that arises is, can we calculate the continuous time Fourier transform of periodic signals? Yes, we can calculate if impulses are allowed in the frequency domain. So, I can write like this, that CTFT, what is the purpose of finding CTFT, continuous time Fourier transform? To know the frequency component present in the signal. So, I am going to write here, CTFT can be applied to periodic signals if impulses are allowed in the frequency domain. If impulses are allowed in the frequency domain, Now, how we are going to find out the continuous time Fourier transform of periodic signals? We have one expression, you can use that expression to find out the Fourier transform, that is given by x of omega is equal to summation n varying from minus infinite to plus infinite 2 pi Cn into del of omega minus n omega naught. You can use this expression to find out the continuous time Fourier transform of periodic signals, where here Cn is the exponential Fourier series coefficient. Cn is what? Exponential Fourier series coefficient, which can be calculated by making use of the expression 1 by t over the period t0 to t0 plus t, x of t multiplied with e power minus jn omega naught t dt. You can use this expression to find out the value of Cn, and omega naught is the fundamental frequency given by 2 pi by t. So, dear students, if you are given a periodic signal, simply find out the value of Cn using this expression. After that, you can substitute here, so that you will get the Fourier transform of periodic signals, right? And is there any easier way to find out the value of Cn? Yes. Now, this Cn can be calculated like this. Here, if you observe this integral, what is this integral? This integral looks like Fourier transform, yes or no? But in the place of omega, I have n omega naught. So, I can write this integral as capital X of n omega naught divided by t. So, if you are given a periodic signal, select one proper period. In that period, observe what is the signal present. For that signal, calculate the Fourier transform. In that Fourier transform, replace omega with n omega naught, divide with t, so that you will get Cn. After getting the value of Cn, substitute here, so that you get the Fourier transform of periodic signals. Again I am saying, if you are given a periodic signal, select one proper period. In that period, observe what is the signal present. For that signal, calculate the Fourier transform. In that Fourier transform, replace omega with n omega naught divided by t, so that you will get the value of Cn. After getting the value of Cn, substitute here, so that you get the Fourier transform of periodic signals, right. Suppose if you are having a doubt how this expression came, very easy. See, if you want to know the origin of this expression, you can do one thing. In this slide only I will do. So let us move this towards left like this, yeah, right. Now if I ask you one question, what is the continuous time Fourier transform of e power j omega naught t? What is your answer? E power j omega naught t, you might have studied. Continuous time Fourier transform is 2 pi into del of omega minus omega naught. If I ask you what is the continuous time Fourier transform of e power j 2 omega naught t? 2 pi into del of omega minus 2 omega naught. Or in general, if I ask you what is the continuous time Fourier transform of e power j n omega naught t, what is your answer? Your answer will be 2 pi into del of omega minus n omega naught. And we know that periodic signals can be represented using Fourier series, and in particular if I take exponential form of Fourier series, is given like this: summation n varying from minus infinite to infinite Cn e power jn omega naught t, where Cn is the exponential Fourier series coefficient. Now what happens if I apply Fourier transform on both sides? This becomes summation n varying from minus infinite to infinite. Cn is a constant value, exponential Fourier series coefficient. What is the Fourier transform of e power jn omega naught t? Del of omega minus n omega naught. Sorry, e power jn omega naught t, what is the Fourier transform? Cn is the exponential Fourier series coefficient, e power jn omega naught t, 2 pi into del of omega minus n omega naught. Now you can compare this expression with this one, right, both are same. So simply apply the Fourier transform to the exponential Fourier series expression. If you are going to apply the Fourier transform to this expression, yes, you are going to get the Fourier transform of periodic signals. And I told you now how to calculate the value of Cn. Select one period, in that period observe what is the signal present. For that, calculate the Fourier transform. In that Fourier transform, replace omega with n omega naught, divide with the period, you will get the Cn, and after getting the value of Cn, simply substitute here. Now we will do one thing. Let us solve one example. Example is like this. CTFT of, we have to find out the CTFT of impulse train. CTFT of impulse train. Right. How to find out this one? We will do one thing. Let us draw impulse train signal first. Impulse train signal in time domain can be given like this. So here I am going to take one impulse, area strength is 1. If I am going to take one more impulse here at a t, this becomes del of t minus t. I will take one more impulse here at 2t, so del of t minus 2t, and so on. I will take one more impulse here, this becomes del of t plus t, and so on. This is my impulse train of impulses, and the other name for impulse train is what? Dirac comb. Impulse train or other name is Dirac comb. If you observe this one, if you observe this signal, this is a periodic signal. Now let us find out the continuous time Fourier transform. For that, first of all, let us calculate the period. Period is how much here? T. Omega naught is 2 pi by t. 2 pi by t. Right? And If you want to calculate the continuous time Fourier transform, we must find out the exponential Fourier series coefficient. For that, what I said, select one period, I said, select one period, and here I am going to select the period as this one. My choice of period is from minus t by 2 to t by 2, which is also t. My choice of period is from minus t by 2 to t by 2. So, here I will write choice of period, choice of period is minus t by 2 to t by 2, minus t by 2 to t by 2. And what I said, how to calculate the exponential Fourier series coefficient Cn. So, select one period, selected, in that observe what is the signal present. What is the signal present? Impulse signal is present. For that, calculate the Fourier transform. Fourier transform of impulse signal is 1. In that, replace omega with n omega naught. 1 means, is there an omega to replace with n omega naught? No. So, 1 remains as it is, and divide with the period. Period is t here. So, exponential Fourier series coefficient in the case of impulse train is a constant value 1 by t, 1 by t. Now, after getting the value of Cn, what we have to do? We have to substitute that Cn here, right. Now, what will happen if I substitute? X of omega is equal to summation n varying from minus infinite to plus infinite 2 pi Cn, 2 pi Cn means 2 pi by t into del of omega minus n omega naught is 2 pi by t. This is the Fourier transform I got. Now, what I want to do is, I want to plot this Fourier transform. Yes, you can plot. So, here I am going to plot. Now, what happens here if I substitute n is equal to 0, 2 pi by t into del of omega, 2 pi by t into del of omega means this is del of omega weighted by 2 pi by t. Here 2 pi by t is the area or strength of the impulse in frequency domain. Now, what happens if I substitute n is equal to 1? Del of omega minus 2 pi by t, omega minus 2 pi by t, n is equal to minus 1, omega plus 2 pi by t, n is equal to 2, del of omega minus 4 pi by t, minus 2, minus 4 pi by t, like this. So, this is the Fourier transform what we are going to get. Now, if you observe, if this is a train of impulses, if this is a train of impulses in time domain, this is also train of impulses in frequency domain. So, what can you say? We can say that Fourier transform of impulse train is again impulse train. So, we can write impulse train signal forms a Fourier transform pair with impulse train only. This is the Fourier transform of impulse train, right. Now, observe here, we are going to make use of this Fourier transform of impulse train in the concept of sampling. Along with this Fourier transform of impulse train, you need some more concepts of Fourier transform in order to master sampling. What are those? See, you need convolution in time domain, property of CTFT, continuous time Fourier transform. Convolution in time domain property of CTFT. What does it say? It says that if the signal x of t forms a Fourier transform pair with x of omega, impulse response h of t forms a Fourier transform pair with h of omega, then if you are going to convolve these two signals in time domain in order to get the output of LTI system, so convolution in time domain is equivalent to multiplication in frequency domain. Convolution in time domain is equivalent to multiplication in frequency domain, right. This property you must know, and here this h of omega which we obtained by taking the Fourier transform of impulse response is what is known as frequency response. Remember, Fourier transform of impulse response gives frequency response, which tells us the filtering capability of the system. Frequency response tells us the filtering capability of the system. This property you must know. And one more important property is convolution in frequency. This property also you must know. Convolution in frequency. What does this property say? This property says that if x1 of t forms a Fourier transform pair with x1 of omega, x2 of t forms a continuous time Fourier transform pair with x2 of omega, and if you are going to multiply the signals in time domain, we must convolve them in frequency domain. Convolve them in frequency domain. Right. So this is what is your convolution frequency property, or this property is also known as multiplication property. Also known as multiplication property, because the signals are multiplied in time domain, right. So if you are comfortable with these two properties, yes, we can proceed for sampling, right. So let us discuss the sampling operation. Sampling operation. And the kind of sampling what we are going to discuss here is impulse train sampling. Impulse train sampling. How we are going to explain this impulse train sampling? Observe here. First of all, what is the purpose of sampling? The purpose of sampling is to convert a continuous time signal into a discrete time signal. So the purpose of sampling is to convert a continuous time signal into a discrete time signal. How that is done? Observe here. In order to sample a continuous time signal, what I am going to do is, I am going to take a multiplier. I am going to take a multiplier. What is the purpose of this multiplier? To multiply the input signals. One input to the multiplier is the continuous time signal, which I want to convert into a discrete time signal. One input to the sampler is the continuous time signal, and the other input to the multiplier, is the impulse train signal, what we have seen just now. Impulse train signal. The distance between adjacent samples is Ts. So impulse train signal like this. And this impulse train signal can be denoted with del Ts of t. Del Ts of t. Now these two signals are multiplied in the multiplier, so that I am going to get the sampled signal denoted by x sampled of t, which can be shown like this. Here we must recollect one important property of impulse signal, that if you are going to multiply the impulse signal with other signal, we will get the same impulse signal. But its area will change. Before multiplication, look here, before multiplication, area of this impulse placed at 0 was 1. After multiplication, this area gets multiplied with the value of the signal at that instant. Okay. So here also, at Ts also, impulse will come, but its area will change according to the signal. Okay, according to the signal. Here the signal value becomes the area, because this area is 1, no, here the signal value becomes the area of the impulse, right. As the area of the impulse here is 1, this gets multiplied with the value of the signal, so that we are going to get this kind of signal, right. This is my x sampled of t, In this way sampling operation is done. Now if you observe mathematically, if you want to observe mathematically, now can I write x sampled of t as x of t multiplied with the impulse strain del Ts of t. Del Ts of t is the impulse strain. Can I write like this? Yes, I can write. Now observe here, x sampled of t is x of t multiplied with del Ts of t. Impulse strain mathematically can be written like this, summation n varying from minus infinite to infinite del of t minus nTs. Del of t minus nTs. Can I write in the form of a summation? Yes. Now observe here. After this, let us use one important property called product property. Product property of impulse says that if I multiply the signal x of t with del of t minus t naught, okay, what is that I am going to get? I am going to get the same del of t minus t naught, but its area will change according to the signal x of t naught, right. By making use of this product property, yes, how I can simplify my x sampled of t as, here if I multiply my x of t with this impulse strain, I am going to get the impulse strain only. I am going to get the impulse strain only, but the area of the impulses in the impulse strain will change according to the signal x of nTs into del of t minus nTs, x of nTs del of t minus nTs. This is what happens in time domain. See, in time domain simply multiply your signal with impulse strain to get a discrete time signal. Now let us observe this effect in frequency domain, right. So how to convert a time domain signal to frequency domain? Apply Fourier transform. And what property of Fourier transform you are going to apply here? If you observe, the signal and the impulse strain are multiplied in time domain. The signal x of t and impulse strain are multiplied in time domain, means in frequency domain they are convolved. They are convolved. So you are going to apply the multiplication property or frequency convolution property what we have seen just now, right. x1 of t multiplied with x2 of t forms a continuous time Fourier transform pair with 1 by 2 pi x1 of omega convolved with x2 of omega. Now x sampled of omega, which is nothing but the Fourier transform sample signal becomes 1 by 2 pi. Why this 1 by 2 pi factor came? Because from the property x of t Fourier transform is x of omega, multiplication is done in time domain, convolution in frequency domain. What is this second signal? Impulse strain. And what is the Fourier transform of impulse strain? Impulse strain only. So we have seen now Fourier transform of impulse strain is impulse strain only, summation n varying from minus infinite to infinite del of omega minus n omega s will come, right. Now here I can cancel this 2 pi or x sampled of omega here is 1 by ts summation n varying from minus infinite to infinite. Now we have to convolve. What is the convolution of a signal with a shifted impulse? What is the convolution of a signal with a shifted impulse? Shifted signal. Convolution of a signal with a shifted impulse is a shifted signal. Now the expression what we got here, this is what is known as the Fourier transform of sampled signal. This is nothing but this is a sampled signal and this is a Fourier transform of sampled signal which we call by the name sampled spectrum. What we call? Sampled spectrum. Fourier transform of sampled signal which we call by the name sampled spectrum, very important. Now if you observe this sample spectrum, or after getting the sample spectrum, if I observe this overall sampling process, what is the variable in the sampling process? The distance between adjacent samples, Ts is the variable. Generally we will sample here and we will get the sample signal, and remember, after getting the sample signal, we must be in a position to reconstruct the original signal from the sample signal. After getting this one, we must be in a position to reconstruct the original signal from the sample signal. Reconstruction means if you are going to join the tops like this, you must get the shape of the original signal, and that depends on the values of Ts. See, if your Ts is very small, if you are going to join like this, you will easily get the shape of the original signal. Whereas if Ts values are very far apart, so if you are going to join like this, you may not be able to get the shape of the original signal. So here the reconstruction depends on the values of Ts. Can I say that? Yes. And here Ts is known as sampling period. Ts is known as sampling period or sampling interval. And can I say one more important point, that as we are going to vary the sampling period Ts, the sampling frequency given by omega s is equal to 2 pi by Ts is also going to vary. Yes, as we are going to vary the sampling period Ts, the sampling frequency given by 2 pi by Ts is also going to vary. So what is the optimum value of Ts or what is the optimum value of omega s you are going to select is the question, so that we can easily reconstruct the original signal. So we must search for this value. So what is our aim now? We must look for a optimum value of Ts or optimum value of omega s such that we can easily reconstruct the original signal. For that, in order to observe the values of Ts or omega s, one point I am going to write here, that is consider that our signal, consider a band limited signal x of t. Consider a band limited signal x of t. Band limited signal means, that is x of omega is 0 for mod omega greater than omega m. Band limited signal means x of omega is 0 for mod omega greater than omega m. See, x of omega is 0 for mod omega greater than omega m is this kind of situation. Why we are going to consider a band limited signal? Why we are going to consider band limited signal? Because remember, most of the information or important information in any signal lies in the low frequency components only. High frequency components do not carry significant information, so that we are eliminating the high frequency components by band limiting, limiting in band, limiting in frequency. How to band limit a signal? Simply pass the signal through a low pass filter. Simply the high frequency components will be eliminated. Now what is the optimum value of Ts or what is the optimum value of omega s we are going to select is the question, right? For that we will examine various cases, after that we will come to a conclusion. Now case 1 is, what happens if I am going to consider my sampling frequency omega s such that it is greater than twice the highest frequency component present in the signal. What happens if I am going to consider my sampling frequency omega s such that it is greater than twice the highest frequency component present in the signal? Whether I can reconstruct or not, we will see. How to verify this one? As we are going in frequency domain, we got the sample spectrum now. In this sample spectrum, in the place of omega s, substitute this value. So omega is greater than 2 omega means you can take some value 3 omega. Now what happens to your sample spectrum? X sample of omega is equal to 1 by Ts summation n varying from minus infinite to infinite x of omega minus n omega s. Omega s is 3 omega m. Now let us draw the spectrum by giving different values of n. How to draw? What happens if I substitute n is equal to 0? What happens if I substitute n is equal to 0? I will get x of omega, means this original spectrum, but weighted by 1 by Ts. This kind of spectrum I am going to get, minus omega m to 1 by Ts. What happens if I substitute n is equal to 1? I will get x of omega minus 3 omega m, means delayed version of x of omega by 3 omega m, means centered around 3 omega m. 3 omega m plus omega m is 4 omega m, 3 omega m minus omega m is 2 omega m, and the spectrum repeats like this for different values of n. What happens if I substitute n is equal to minus 1? We will get x of omega plus 3 omega m. So this is x of omega plus 3 omega m weighted by 1 by Ts, and the spectrum repeats, right? And you can observe from this spectrum, what is our aim? Our aim is to reconstruct the original signal. Reconstructing the original signal means what? Reconstructing the original signal means what? From this periodical repetition, isolating this spectrum centered around 0. From the periodical repetition, if I can isolate the spectrum centered at 0, yes, it is equivalent to reconstruction. So how we are going to isolate this one? By passing this periodical repetition through a low pass filter whose characteristics are like this. If I pass this periodical repetition through a low pass filter whose characteristics are shown by the pink dots, yes, we can get your spectrum back, means reconstruction is possible. And one more advantage with this case is you can observe that there is some space here between this omega m and 2 omega m, which is preventing these frequencies to overlap, which we call by the name God band, And the case where we assume omega s greater than 2 omega m, this case is what is called as oversampling. So observe here, omega is greater than 2 omega m, no problem. Omega is greater than 2 omega m, no problem. Yes, we can reconstruct the original signal, right? Now, and there is a provision of God band also. Here, let us examine case 2. Case 2, where omega s is 2 omega m. Omega s is equal to 2 omega m. We will see whether we can reconstruct or not. Now the process is same. Substitute the value of omega s in the sample spectrum and draw the spectrum. So what happens to your sample spectrum? Example of omega is 1 by Ts summation n varying from minus infinite to infinite x of omega minus n omega s is 2 omega m. Now we will do one thing, let us draw this spectrum also by giving different values of n. Now what happens if I substitute, n is equal to 0, I will get x of omega weighted by 1 by Ts, x of omega means minus omega m to omega m weighted by 1 by Ts. What happens if I substitute n is equal to 1? X of omega minus 2 omega m means shifted version to the right by 2 omega m, means centered around 2 omega m. 2 omega m minus omega m is omega m, 2 omega m plus omega m is 3 omega m. And the spectrum repeats. What happens if I substitute n is equal to minus 1? X of omega plus 2 omega m means centered around minus 2 omega m, the spectrum will come like this, right? Again periodical spectrum I am going to get. Again from this periodical spectrum we can get our original spectrum back by placing the low pass filter like this. This pink line indicates the low pass filter characteristics. But here in the second case, your low pass filter must have a sharp cutoff because God band is absent here. God band is absent here. Reconstruction is possible in this case also, and the case where we assume omega s is equal to 2 omega m is what is known as critical sampling. Critical sampling. Reconstruction is possible here also, right. Now, we will examine the final case, case 3. Case 3, where we consider omega s less than 2 omega m. Omega s less than 2 omega m, right. Omega s less than 2 omega m means, let us consider omega s is equal to some 1.5 omega m. Process is same. Substitute this value of omega s in your sample spectrum. So 1 by Ts summation n varying from minus infinite to plus infinite x of omega minus n omega s 1.5 omega m. Right. Now, by giving different values of n, try to draw the spectrum. What happens if I substitute n is equal to 0? N is equal to 0 means x of omega weighted by 1 by Ts. What happens if I substitute n is equal to 1? X of omega minus 1.5 omega m you will get. So 1.5 omega m is centered around 1.5 omega m. 1.5 minus 1, 0.5 omega m, 1.5 plus 1, 2.5 omega m, and if I substitute n is equal to minus 1, so centered around minus 1.5 omega m, this kind of spectrum or periodical repetition you are going to get. So if you observe here, there is overlap of frequencies here. Overlap of frequencies which we call as aliasing or aliasing, due to which we cannot reconstruct our original spectrum back, because if you are going to place the low pass filter here, along with the required components, some unwanted components are also coming. So reconstruction is not possible here, and the case where we assume omega is less than 2 omega m is what is known as undersampling. What it is known as undersampling. So this is what is your overall sampling process, and from this sampling process we can notice some important points. What are those? The first point is, if you observe case 1, case 2, case 3, in case 1, case 2 and case 3 we are going to get periodical repetitions. Periodical repetitions in what domain? Frequency domain, and we are going to sample in time domain. And the statement what we can give here is that if you sample a signal in time domain, periodical repetition will occur in frequency domain. If you sample a signal in time domain, periodical repetition will occur in frequency domain, and if you sample a signal in frequency domain, periodical repetition will occur in time domain. Okay, that is the first point. So let me write, if we sample a signal, in time domain, periodical repetition will occur in frequency domain. And if we sample a signal in frequency domain, periodic repetition will occur in time domain, will occur in time domain, right? Fine. This is the first point to be noted. And the second point is, see in which of the cases you can retrieve your original spectrum back, the first case and second case, right? Third case we cannot reconstruct. So, we can reconstruct the original spectrum if the sampling frequency omega is greater than or equal to 2 omega m, 2 omega m. What is the minimum value here? Minimum value. Minimum value here is 2 omega m. 2 omega m, which is known as the Nyquist rate. What is this is known as? Nyquist rate. Nyquist rate. Okay, and remember this omega s is given by 2 pi fs, or in terms of f we can give like this: fs must be greater than or equal to 2 fm. Fs must be greater than or equal to 2 fm, from which fs minimum is 2 fm. Fs minimum will be 2 fm, and this fs is given by 1 over ts, and this ts is known as Nyquist interval. Nyquist interval, and in terms of ts, ts must be less than or equal to 1 by 2 fm. Ts must be less than or equal to 1 by 2 fm, or the maximum value of ts, the maximum value of ts is 1 by 2 fm, 1 by 2 fm, right? Means the distance between adjacent samples, the maximum space allowed is 1 by 2 fm. So, it can, the distance between adjacent samples cannot be greater than 1 by 2 fm. And after this we can write the statement of the sampling theorem also. Statement. So, whatever the story we have seen, let us write in the form of a single statement. So, this is what is known as the sampling theorem statement. And what does it say? It says that a band limited signal, see for impulse train sampling the signal must be band limited signal. A band limited signal x of t, a band limited signal x of t that is x of omega is equal to 0 for mod omega greater than omega m can be reconstructed from the samples x of nts where n is equal to 0 plus or minus 1 plus or minus 2 and so on provided omega is greater than 2 omega m. Generally we will go for oversampling only we will go, provided omega is greater than 2 omega m, where omega s is equal to 2 pi by ts, where omega s is equal to 2 pi by ts. This is the statement of the sampling theorem. Now we will do one thing. Before leaving the topic, we will see whether we can find out the Nyquist rate for some signals or not. Suppose a question was asked like this: x of t is equal to sine 4000 pi t by pi t. Now we have to find out the Nyquist rate and Nyquist interval for this signal. How to find out? See, Nyquist rate means what? Nyquist rate means, if you observe, look here, Nyquist rate means twice of omega m. Omega m means what? Highest frequency component present in the signal. Highest frequency component will be present in what domain? Frequency component is present in frequency domain, but the given signal is in what domain? Time domain. So in order to get the highest frequency component, we must convert the time domain signal to frequency domain. How to convert? Apply Fourier transform. What Fourier transform you have to apply? You can utilize one important concept, that sin at by pi t, sin at by pi t forms a continuous time Fourier transform pair with rectangular pulse varying from minus a to a in frequency domain. Now what is there in place of a here? 4000 pi. So sin 4000 pi t by pi t forms a continuous time Fourier transform pair with rectangular pulse varying from minus 4000, k means 1000, to 4000. Now from this I got the highest frequency component. What is that? Omega m 4000 pi. I can calculate the Nyquist rate. 8000 pi, units are radians per second, and omega s is what? 2 pi fs now. So what is fs? 4000 hertz from this, if you compare these two. And what is ts? 1 by 4000 seconds. In this way you are going to find out the Nyquist rate and Nyquist interval. Suppose one more question was asked like this. If one more question was asked, xt is equal to some sin 4000 pi t by pi t whole square. Now how you are going to get the Nyquist rate and Nyquist interval? Xt is equal to, how I can write this one? Sin 4000 pi t by pi t multiplied with sin 4000 pi t by pi t. The principle involved is same. To the time domain signal, apply Fourier transform, get the highest frequency component. Twice the highest frequency component gives you Nyquist rate. So what is the Fourier transform for this one? Rectangular pulse varying from minus 4000 pi to 4000 pi. Here also what is the Fourier transform? Rectangular pulse varying from minus 4000 pi to 4000 pi. If you observe, these two signals are multiplied in time domain. In frequency domain they will be convolved. What is the convolution of two rectangular pulses of equal bits? Triangular pulse will get. And we know that the range of output in convolution is from sum of lower limits to sum of upper limits, means minus 8000 pi to 8000 pi. So that I got the highest frequency component 8000 pi. So omega m is 8000 pi, Nyquist rate omega s is 16000 pi radians per second, fs is 8000 hertz, ts is 1 over s fs, 1 by 8000 seconds. In this way we are going to find out the Nyquist rate and Nyquist interval, and this is about the impulse train sampling. Sampling is not completed, we can discuss many problems in sampling, and if you want such beautiful discussions, please contact SAIMEDHA Koti, Hyderabad. Thank you.